Nuclear physics is a very new and fascinating branch of physics which deals with the atomic nucleus. The atomic nucleus is the small, dense region consisting of protons and neutrons situated in the center of an atom. The branch of physics which deals with the atom is called atomic physics. The discovery and development of atomic physics begins with the discovery of the atom, a word that comes from the Greek atmos, meaning individual. An Indian sage and philosopher, Acharya Kanad, was the first person who formulated the concept of atoms nearly 600 years prior to the birth of Christ. Acharya Kanad called that individual particle Parmanu, which literally means atom. But the theory given by Kanad had not any strong evidence, and after 2500 years later in early 1800s, an English scientist, John Dalton, gave the first evidence-based theory of atom. That was a marvelous scientific breakthrough during that time. Until that time, it was believed that everything in our universe is composed of these individual particles. But there was beginning to be a belief that maybe the atom did have more than one part. Finally, in fact, in 1897, J.J. Thomson, an English physicist, discovered what was eventually called an electron. He identified it as part of an atom. He proved that electron is almost 2000 times smaller than the smallest atom, hydrogen, and that it had a negative electric charge. He believed it orbited around the rest of the atom like the Earth around the Sun. Meanwhile, in 1985, a French scientist, Henri Becquerel, discovered radioactivity, and it was the time when the journey of nuclear physics started. After that discovery, a lot of research was done in radioactivity by Ernest Rutherford, Paul Billard, Marie Curie, and Marie Curie. In 1899, Rutherford was the first who described the alpha particle. He found that alpha particles are spontaneously emitted by radioactive substances like uranium and radium. Finally, we entered the 20th century with respect. That was the state of our knowledge of atoms. We had discovered atoms experimentally. At that very beginning of the 20th century, in 1905, a theoretical physicist came into existence. A young German, Albert Einstein, had a new PhD degree, was brilliant in math and physics. But he had failed to get the teaching job he had hoped for and had to settle for a position as a patent clerk in Bern, Switzerland. His work there did give him time to think about the world around him. He published 5 of his famous theories that year. During his study of special relativity, Albert Einstein found that mass and energy are equivalent and that they can be converted back and forth between one another. He gave the famous equation E equal to mc squared, which is critical to the study of nuclear physics because nuclear interactions are all about mass-energy conversion. In the formula E is equal to mc squared, E is the energy, m is the mass, and c is the speed of light. So if you have 1 kilogram of any matter, then the energy contained in that matter will be 25 billion kilowatt hours. That is equal to the 6 times the electrical energy consumed by Delhi in 1 month. But at that time, no one, including Albert Einstein, had any idea that how do we release that energy. The E equal to mc squared just said if mass disappeared, it would be replaced by energy. After a few years later, around 1908 to 1913, Geiger and Marson did the series of experiments under the direction of Ernest Rutherford in which they bombarded the alpha particles on a very thin gold foil, and they observed that vast majority of those alpha particles went undeviated, while few of those alpha particles experienced huge amounts of deviation. From the outcomes of those experiments, Rutherford gave the famous theory which is known as Rutherford's atomic model. It concludes that almost all the atomic matter is concentrated in a tiny volume situated at the center of the atom, called the atomic nucleus. People could have realized the existence of atomic nucleus for the first time in history after the success of this model. The credit for the discovery of proton also goes to Rutherford. In 1917, he proved that the hydrogen nucleus is present in all other nuclei, and so he thought that nucleus of the hydrogen atom should be one of the fundamental particles in the nuclear world, and hence he named this particle proton, because in Greek the word proton means first. Till then, nucleus and proton had been discovered, but people didn't know exactly about the neutron. Up to the 1930s, people had thought that atomic nucleus consists of protons and nuclear electrons. This idea appeared quite reasonable, but it was made clear that it contained serious difficulties. Meanwhile, in 1912, J.J. Thomson discovered that neutral neon gas is a mixture of two kinds of elements having different atomic weights. Afterward, a precise mass spectroscopy analysis was done by F.W. Aston, which confirmed that many elements are mixture of two or more kinds of isotopes having different atomic weights. This means that there exist different nuclei having the same electric charge but different masses. Therefore, it was predicted by Rutherford that there exists an electrically neutral particle in the nucleus with almost the same mass as a proton, so that the existence of isotopes could easily be understood. Rutherford talked about this idea to his students in his lecture. One of his top students, James Chadwick, influenced strongly by him and finally got the honor of discovering that particle in 1932. Chadwick named it neutron. The discovery of the neutron was the extraordinary development in atomic and nuclear physics in the first half of the 20th century. Proton and neutron are collectively called as nucleons. They have almost the same mass but different electric charges. Proton have one electronic charge and neutron has no charge. Now if you take two protons and bring them very close to each other up to a distance of around 1 femtometer, then you can calculate the Coulombic force of repulsion that exists between these two protons will be around 230 newtons. It is a huge amount of force, but still nucleons are situated in an atomic nucleus. So something is there which is much more powerful than this kind of Coulombic repulsion, and this connects with the discovery of the nuclear force. The nuclear force is a strong force between nucleons which is attractive at its maximum around a distance of around 1 femtometer, and beyond that it decreases exponentially and becomes almost zero beyond 2.5 to 3 femtometers. The interesting thing is that for the distance less than 1 femtometer, this force suddenly decreases and becomes repulsive for a distance of fewer than 0.8 femtometers. This force is repulsive at a very low distance is highly interesting, because otherwise the neutrons and protons which are experiencing such a heavy attractive force can be collapsed onto itself. After that, scientists started thinking about the mechanism that leads to this kind of complex nature of a nuclear force. In 1935, a Japanese scientist, Hideki Yukawa, was given a successful theory of nuclear forces known as Yukawa theory or meson theory, and tried to explain how nuclear forces hold a nucleus. He considered that the nuclear force is due to the exchange particle mesons between neighboring nucleons. Meanwhile, in 1929, a Russian-born American physicist George Gamow formulated a nuclear model called the liquid drop model. According to this model, the nucleons in a nucleus behaves like the molecule in a drop of liquid. And if a sufficient amount of extra energy is given to the nucleus, the spherical nucleus may be distorted into the dumbbell shape, and then it splits into two nearly equal fragments, releasing some energy. It was the first nuclear model that provides excellent estimates of the average properties of nuclei. This model explains the binding energy of a nucleus. At that point of time, another model of nucleus came into existence, which is Fermi gas model. It is a statistical model of the nucleus which considers that protons and neutrons are moving freely within the nuclear volume. That is, nucleons are not interacting with each other. The model assumes that nucleons are filled into the lowest possible energy states available to them up to the Fermi energy in a manner consistent with the requirement of Pauli exclusion principle. It explains why beta decay happens and why there are almost equal number of protons and neutrons inside a nucleus. After that, in 1938 to 1939, nuclear fusion and nuclear fission were discovered by some German scientists. That research made the development of an atomic bomb a theoretical possibility. And people thought that it would first be made by Germany. But after a few years later, on December 2, 1942, the world's first self-sustaining controlled nuclear chain reaction took place at the University of Chicago's football stadium. 49 scientists led by Enrico Fermi were present for the event. It was the time when World War II was started. At that time, the United States started a project known as Manhattan Project with the support of United Kingdom and Canada for the purpose of research and development. And they successfully made the atomic bomb in 1945, which became the reason for the end of World War II. So we finally entered into an era of modern nuclear physics when most of the countries had started to do something new and exciting in the field of nuclear physics. Before 1949, physicists only knew about the configuration of electrons in an atom, but they didn't know exactly how nucleons are arranged in a nucleus. And this question gave birth to a very famous shell model. The shell model is partly analogous to the atomic shell model, which describes the arrangement of electrons in an atom. After adding nucleons to a nucleus, there are certain points where the binding energy of the nucleus is significantly high than the last one. At those points, either the number of protons or number of neutrons or both are equal to 2, 8, 20, 28, 50, 82 or 126. And these numbers are called magic number. At the magic number, nuclei are highly stable and it is the origin of the shell model. The shell model is based on the assumption that nucleon in a nucleus moves in an effective attractive potential formed by all other nucleons. The nuclear spin and parity of nuclear states are easily predicted when a single nucleon changes their orbit. So this model is also known as single particle shell model. But what if the many nucleons involved in a nuclear transition? So for this purpose, nuclear theorists keep refining the shell model to understand the details of nuclear structure and to make the knowledge available for applications in nuclear technology. In 1951, Age Bohr, the son of Niels Bohr, worked with Ben R. Mottelson to relate collective properties of nuclei to the motion of their constituent nucleons. James Rainwater also worked on this topic, and the credit for the discovery of nuclear collective model was given to all of them. In the shell model, nuclear energy states are calculated on the basis of single nucleon moving in a potential well produced by all the other nucleons. But in the collective model, nuclear energy states as well as the magnetic and electric properties of nucleus are explained by the motion of all the nucleons outside the closed shell combined with the motion of the paired nucleons in the core. Meanwhile, during the Manhattan Project, Enrico Fermi proposed an idea of hydrogen bomb to his colleague Edward Teller. There was a physicist, Stanislaw Ulam, who was a co-worker of Teller, made the first key conceptual leap towards a workable fusion design. And finally, Teller and Ulam had given a configuration for the hydrogen bomb. On November 1, 1952, that configuration was tested at full scale at an Iceland in the Enewetak atoll, which was almost 450 times powerful than the bomb dropped on Nagasaki during World War II. After that, we also had the discovery of proton therapy at Berkeley in 1954, experimental evidence for the antineutrino by Reynes and Coban in 1956, nuclear superconductivity by Bohr, Motelson and Pines in 1958, the quarks proposed by Gell-Mann and Gibbs in 1964, discovery of neutron star by Heavis, Klosky and Bell in 1967, discovery of the gluon by DESY in 1978, neutrino oscillations by Super Kamiokande and SNO in 2001, and lots of other things that created a very distinct branch of physics which is today known as the nuclear physics. So now let's talk about the different branches of nuclear physics. Since science moves ahead of both in theory and in experiments, so you can divide the study of nuclear physics mainly into two branches, the theoretical nuclear physics and experimental nuclear physics. While studying the nucleus, we basically study the different kinds of nuclear properties like its size, mass, spin, angular momentum, magnetic moment, etc. In the nuclear model, we study about the different kinds of models that explain certain phenomena and properties associated with the nucleus of the different mass regions. Because there is a drastic change in the overall behavior of nuclei if we go from one mass region to another mass region. Here we study the liquid drop model, the Fermi gas model, the shell model, the collective model, and many more. In theoretical nuclear physics, we study different kinds of nuclear reactions. As radioactivity is a kind of nuclear reaction, so in this part we study different kinds of radioactive decays, like alpha decay, beta decay, gamma decay, different kinds of beta decay, electron capture, proton emission, neutron emission, cluster decay, etc. And also study the kinematics associated with these decay processes. Here we also study the other kinds of nuclear reactions that can be induced artificially in an experiment by bombarding two particles together. Now for the verification of theories, you must have the idea of experimental nuclear physics that deals with the development of new technologies that can induce different kinds of nuclear reactions. For this, we need to create powerful tools that can help us in studying different kinds of nuclear properties and the structure of nuclei. You can divide this branch of experimental nuclear physics mainly into two parts, instrumentation and nuclear experiments. In the instrumentation part, you study the particle accelerator, different kinds of detectors, data acquisition and target making. The particle accelerator is a device that accelerates charged particle using electromagnetic fields. It accelerates the projectile to attain high energy before hit into the target nuclei. In a particle accelerator, radio frequency cavities boost the particle beams while magnets focus the beams and bend their trajectory. So for this purpose, the different kinds of accelerators have developed over time, like linear accelerator, which is also known as Van de Graaff accelerator, cyclotron, synchrotron, and so on and so forth. When energetic projectile nuclei hit a target, then different kinds of particles emerge, and we use different kinds of detectors that can detect the energy and the momentum of the particles that emerge out of a nuclear reaction. The selection of the detectors is based on the particles as well as their energies we want to detect. In this section, we study different kinds of detectors. We have GM counters that can detect alpha, beta and gamma radiation but unable to distinguish between them. We have scintillation detectors like sodium iodide and bismuth germanate, which is used for suppressing unwanted background. It is also used for radiation monitoring in research and in medical imaging equipment. We have silicon detectors that can detect low energy charged particles like an alpha particle and X-ray up to about 20 kilo electron volt in energy. We have high purity germanium detectors used to measure gamma rays energies from 10 kilo electron volt to a few mega electron volt with the high resolution. We have very advanced Clover detectors where one Clover detector is equivalent to 5 high purity germanium detectors. We have BF3, that is boron trifluoride, which can detect neutron. We have Cherenkov counters to detect neutrinos. The data acquisition is also a very important topic to study because the aim of nuclear physics experiment is to gather data about nuclear interactions. The particles that emerge out of nuclear reaction pass through detectors which generate electrical signals. These electrical signals contains information about the particle's energy, trajectory, etc. We need to store this information in a particular digitized format such that it can be retrieved for later analysis. And the data acquisition system actually helps us in this work. Another important topic is the fabrication of the target. In this part, we learn different techniques for the making of nuclear physics targets. We have the rolling method to make a rolled foil and have evaporation techniques of resistive heating and electron gun method to make a evaporated target. Now if you talk about the nuclear experiment, then it can be further divided into 3 parts on the basis of measuring of the physical quantities. The first one is the study of nuclear reaction. Here we study the different kinds of experiments that need to perform for the measurement of charged particle multiplicity, neutron multiplicity, fission cross-section, ER cross-section, breakup reaction, direct reaction, etc. The second one is the gamma ray spectroscopy. It is the quantitative study of the energy spectra of gamma ray sources. Here we study the different kinds of experiments that need to perform to develop the level schemes of nuclei that emits gamma rays in the experiment. And the third one is the study of nuclear structure. Here we study the different kinds of experiments that need to perform for the measurement of lifetimes, B2 values, quadrupole moments of high spin excited states to predict the shape and size of the nuclei. Apart from this, there are many more things to study in nuclear physics. For example, you have the applications associated with nuclear physics like nuclear reactors, nuclear batteries, nuclear weapons, and many more. So this is all about the brief introduction of nuclear physics. From this video, I just started a series of lectures of nuclear physics. In the upcoming video on this series, I will discuss all the topics of nuclear physics in detail. So keep learning with eVigyan, a platform that provides you the knowledge of science. Thank you so much.